In our second lecture dealing with the ideal gas equation, let's review what we've seen so far. We know that the ideal gas equation is PV equals nRT, and it does not involve an actual change in variables, but is actually extremely powerful because hidden within this, we've learned that we can calculate, for example, the density of gases. And from the density of gases, we also know that we can ultimately solve for things like mass or even molar mass. This means we can identify a gas just by knowing some of its basic properties. We only have to know the pressure, the temperature to solve for, or even the R values to solve for many, many different things about gases. What this is going to get to eventually, for example, with molecular mass, is going to be stoichiometry. There is a very important link now between the ideal gas law and stoichiometry because I can solve for N, number of moles, which also leads to mass or molecular mass or molar mass. I can now link everything we know about stoichiometry, all the dimensional analysis, all the solving for products or reactants into gases. So let's take a look at that here. Because mole is that variable, this super important variable, we can now link all of our ideal gas law information to stoichiometry. This is what we did as freshmen, if I had you, when we did the airbag lab, when I asked you to calculate the amount of baking soda that would be necessary, knowing how much CO2 would fill up the airbag, for example. We can do quite a bit with this. In addition to this, we're also going to briefly introduce Dalton's law of partial pressure. A partial pressure formula is actually really simple. Simply put, if you add up each of the individual gases present in a chamber, you have the total pressure. That's it. That really is it. Unfortunately, that really simple concept can be used in quite a different ways that seem a little bit obscure because it's very conceptual in nature. One thing I want to highlight when it comes down to partial pressure is a very practical method of gathering gases. It can be quite difficult to gather and measure the volume of a gas because they simply expand to fill their containers. So, what do we do? A common way is to collect a gas over water. This allows us to capture the gas, trap it, but also measure it. For example, let's take a look at this little experiment here. Here, we have oxygen being released from heated KClO3. This is the little gummy bear demonstration I do. I heat up potassium chlorate and it releases a large amount of oxygen. Now, what I would do is also put a gummy bear into the whole thing and it'd flare up and look like a little bit of rocket. If I didn't do that, I would find that I'm actually producing a fair bit of oxygen gas in the potassium chlorate that I'm heating up. In this apparatus, we have a closed chamber with a pipe allowing the oxygen to escape into an inverted beaker or sometimes graduated cylinder. We commonly use an inverted beaker or graduated cylinder because there are markings on the graduated cylinder or beaker. This is filled with water, and as the gas is allowed to be pumped into it, there is an air bubble that forms right on the top. How big that air bubble is tells me the volume of gas that will be present. The issue, of course, is that there is going to be water vapor present. From our previous discussion with vapor pressure, we know that water and many other liquids are going to vaporize naturally. There's always going to be a small amount of gas molecules in any liquid sample present. So, in the final total volume, there is also a little bit of water vapor present. We do have to use some tables that have been calculated for us that tell us exactly what the vapor pressure of water is going to be under a certain temperature. But if we know that, we merely have to subtract the vapor pressure of water from the pressure inside the chamber. There are charts available for that, and I will provide you with that this week because we have a couple of questions that do involve you removing the water vapor pressure from the chamber. Our first problem I'm going to work with you is 10.55, and this is a stoichiometry problem and the beginning introduction to using moles, grams, and other stoichiometric functions with the ideal gas law. And 10.55, we can see that magnesium can be used as a getter in an evacuated enclosure with the last traces of oxygen. If an enclosure of 0.452 liters has a partial pressure of O2 of 3.5 times 10 to the negative 6 torr at 27 degrees Celsius, what mass of magnesium will react according to the following equation? 2 magnesium reacts with O2 to yield 2 magnesium oxide. In this problem here, we have to calculate the amount of magnesium in grams that will be necessary for these following conditions. Let's take a look at what we know. We are currently given the formula: 2 magnesium plus an oxygen results in 2 magnesium oxide. Let's see what we know from our variables over here. I see that the volume of this chamber and the volume of the gas present is 0.452 liters. Looking through the rest of this, I can also identify the pressure of the oxygen. Keep in mind, this is not the pressure of the magnesium. Magnesium is a solid, but the pressure of the oxygen involved is 3.5 times 10 to the negative 6 torr. I see the temperature as 27 degrees Celsius. We know that has to be in Kelvin, so we add 273, and that results in 300 Kelvin. Because I'm given torr, and I'm most likely going to be using the ideal gas formula, PV equals nRT, I'm going to deduce what some of the other variables are. For example, the R value itself, which I will need for this formula, is going to be based off of torr. Looking at my previous information, I know the R value for torr is 62.36. And then finally, there's the issue of N. Because these variables are given for a gas, this is actually the number of moles of the oxygen that we're going to be solving for. If I know the number of moles of oxygen, then I should be able to use stoichiometry and ultimately solve for the number of moles of magnesium, and then I can convert that to grams of magnesium. But let's deal with the moles of oxygen first. So, taking the ideal gas formula, we know that PV equals nRT. Rearranging the equation for N, dividing both sides by RT, you end up with pressure times volume over RT. Let's plug in our variables. The pressure of the oxygen was given in torr, 3.5 times 10 to the negative 6. The volume of oxygen was 0.452 liters. The R value for torr was 62.36. And then finally, the temperature happens to be 300 Kelvin. When we solve for this, making sure you use the right order of operations, it's product of the top divided by product of the bottom. The number of moles, remember, of oxygen, because these are oxygen's conditions, will be a relatively small number. It'll end up being around 8.45 times 10 to the 11th moles of oxygen. And that is not what is actually being asked for. We are looking for the mass of magnesium. So I need to convert moles of oxygen into grams of magnesium. Let's do that. This is where stoichiometry comes in. 8.45 times 10 to the 11th moles of oxygen, and we'll convert it to grams of magnesium. We'll set up our dimensional analysis box. I'll cancel moles of oxygen. I will convert to moles of magnesium. And from there, I can convert moles of magnesium into grams of magnesium. In a mole-to-mole conversion, I will need the coefficients of the balanced equation. 1 is the coefficient for oxygen. 2 is the coefficient for magnesium. In a mole-to-gram conversion, I know it's 1 mole to the molar mass of magnesium. According to the periodic table, it's 24.3. Solving for this whole thing, you end up with a small amount of grams of magnesium. 4.1 times 10 to the negative 9th grams of magnesium is my final answer. Recapping this problem here, all of my conditions were for a gas. It was for the O2. Once I knew all the conditions for O2, including the moles of O2, I converted moles of O2 into grams of a solid product that they were asking for, magnesium. In 10.57, we'll be dealing with volume, and I'm only going to be working on part A because part B will be part of your homework assignment. 57 begins with the metabolic oxidation of glucose. C6H12 in our bodies produces CO2, which is then expelled from our lungs as gas. The formula is glucose plus oxygen yields CO2 and water. In part A, we're asked to calculate the volume of dry CO2 produced by the body temperature, 37 degrees C, at 0.97 atmospheres when 24.5 grams of glucose is consumed in the reaction here. Here I am given a solid amount of glucose and gaseous conditions. I can use the ideal gas law to solve for the volume of CO2, but I need to know all the variables for the CO2. I must know its pressure, number of moles, and the temperature. Currently, I see that pressure is given to me. I know the temperature is given to me, but the moles of CO2 is not. I do know that I am given 24.5 grams of glucose, and I could convert the grams of glucose into moles of CO2, which would eventually give me my final answer. Let's identify the variables that we currently know. Scanning through this problem, one of the first variables I see is the temperature. That is 37 degrees Celsius. 37 degrees Celsius can't be used. We convert it to Kelvin, which happens to be 310 Kelvin. My next variable happens to be the pressure, 0.97 atmospheres. And then the other variable I see is grams of glucose. This is 24.5 grams of glucose. I will need to eventually convert this into moles of CO2 to be useful for the ideal gas formula. I can also include some other units that aren't immediately obvious. I know I'm going to be using the ideal gas formula, and I will need the R value. As we use atmospheres, we're going to choose the R value for atmospheres of 0.08206. And then finally, we need to solve for volume. And none of this will be in liters. Remember, this is going to be volume of CO2. Before I can begin, I really need to go ahead and take care of that gram issue here. Let's convert this into the gas we're seeking. We are given 24.5 grams of glucose. I want to convert this into moles of CO2 so I can use the ideal gas formula. This is just standard dimensional analysis. Cancel your grams of glucose, convert to moles of glucose. Cancel moles of glucose, convert to moles of the gas we'll be seeking, which is CO2. Here, mole to gram is merely a molar conversion. 1 mole of glucose happens to have a molar mass of 180.18. And then I end with a mole to mole conversion, and this will come from the balanced equation. According to the equation, 1 mole of glucose creates 6 moles of CO2. 1 mole of glucose to 6 moles of CO2. With my problem completely set up, I can now solve. Product of the top divided by product of the bottom. In the end, the number of moles of CO2 is going to be equal to 0.816. Now this, of course, is not a final answer. They were looking for the volume of CO2. This is our unknown. But now I have every variable for the gas. I can plug in all these variables into the ideal gas law and solve for volume. To solve for volume, I divide both sides by pressure. I end up with volume equals nRT over pressure, and now we can plug them in. The number of moles of CO2, the gas we're solving for, is 0.816. The R value is 0.08206, and the temperature happened to be 310. The pressure was 0.97 atmospheres. With all my variables plugged in, I can now solve for volume. The final answer, the volume of CO2 that would be produced from the mass of glucose given, is 21.4 liters of CO2 at those given conditions. In 10.59, another example here. We have an issue with the gas being collected over water. Now, this is actually a common method because gases cannot be collected easily. Most commonly, what we'll end up doing is pumping the gases that are being produced into an inverted graduated cylinder and measuring the water displacement. However, this does mean that there's water vapor present and it must be accounted for. And we're going to use a little bit of total pressure here to solve with 10.59 as well. 10.59 reads, the hydrogen gas is produced when zinc reacts with sulfuric acid. And we have the formula given to us. If 159 milliliters of wet hydrogen gas is collected over water at 24 degrees Cs and has a barometric pressure of 738 torr, how many grams of zinc have been consumed? Now, from the previous problems, this isn't too difficult. Ultimately, I need to find the number of moles of the gas that I can calculate. Here, if I find the moles of hydrogen, I can link the moles of hydrogen to moles of zinc and then solve for grams of zinc. That's not a big issue. The issue, again, is that this is a wet gas. It was collected over water, and it contains water vapor in it. There is pressure of the water vapor as well as the pressure of the gas in this total pressure right here. So let's address that first. Total pressure in this problem is going to be the sum of the pressure of the hydrogen gas that we will care about and the water that was also collected with it. Well, I also know that the total pressure is given to me. The barometric pressure said that was 738 torr. The problem does instruct for me to use the vapor pressure of water as tabulated in Appendix B. The vapor pressure of water is commonly known, and there's very large charts of it. If I refer to this chart, I can find that the pressure of the water at the temperature given to me, which happens to be 24 degrees Celsius, is 22.38 torr. Once again, the reason I know this is because I looked it up. You can find this reference information in what I gave you in Canvas. This means that the pressure of the gas that we'll be solving for, hydrogen, is going to be the total pressure minus the pressure of the water. So let's take the total pressure of 738 and subtract 22.38, and now we know the pressure of the hydrogen gas, which happens to be 715.62 torr. With that out of the way, the rest of the problem is actually relatively easy. I simply need to identify the remainder of the variables given to me. So, scanning through the problem, I see a volume of 159 milliliters of water. We know we can't use milliliters. We need to convert this to liters. Divide it by 1,000, 0.159 liters. I know some of you are thinking, but wait a minute, sir, isn't there water vapor in there? You are correct, but it's minimal and negligible, and we actually can't calculate how much exactly the volume of water vapor is, so we have to assume that that is also simply the amount of hydrogen gas. I can also see the temperature. It was 24 degrees Celsius. A quick conversion to Kelvin results in a temperature of 297 Kelvin. I know I'm going to need an R value at some point. The pressure given to me this time around is in torr. So my R value should be torr. The torr R value is 62.36. And then finally, I simply don't know the number of moles. Remember, we're solving for the gas present, which is the hydrogen gas. If I can solve for the number of moles of hydrogen, then I can solve for the grams of zinc using stoichiometry. So now we have nearly everything necessary to solve. We can plug this into the ideal gas formula. PV equals nRT. We'll solve for moles. N is going to be equal to PV over RT. I will plug in my variables. My pressure is 715.62. The volume is 0.159. The R value is 62.36. And the temperature is 297. Remember to maintain your order of operations. And then you will find that the number of moles of the gas that we're solving for, hydrogen, is a very small number, 6.14 times 10 to the negative 3 moles. Okay, great. Now I know the moles of hydrogen present. Well, let's use that and calculate the grams of zinc. This is regular stoichiometry. So we're going to take the mole of hydrogen and convert to grams of zinc. 6.14 times 10 to the negative 3 moles of hydrogen gas. First thing I will do is cancel moles of hydrogen and convert to moles of zinc. I'm going to use the balanced equation that was given to me. Here, 1 zinc to 1 hydrogen. That's a nice easy 1-to-1 ratio. Then I will cancel moles of zinc and convert to grams of zinc that the problem is asking for. This is molar mass. 1 mole of zinc has a molar mass of 65.39. And then we can solve. Once you resolve this out, you end up with the grams of zinc equaling about 0.402 grams of zinc as our actual final answer. You are going to end this week with a work on partial pressure. Now, the partial pressure formula is actually really simple. It's just adding up all the individual pressures to get a total pressure. There's nothing else to it. Surprisingly, though, as simple as it is, you can actually end up with quite a few complex problems about partial pressure. So I'm going to take a look at 10.61. However, I'm not going to complete all of this because this is actually part of your assignment. In 10.61, I'm really going to give you some hints and some assistance with this. Consider the apparatus shown in the following drawing. So we have 2 chambers, one filled with nitrogen, one filled with oxygen. They both have a different volume, 2 liters of nitrogen, 3 liters of oxygen. They have a different atmosphere. However, they have the same temperature, and that's good. There's a valve in the middle. When the valve between the 2 containers is opened and the gas is allowed to mix, how does the volume occupied by the nitrogen gas change? And what is the partial pressure of nitrogen after the mixing? So let's take a look at 61A over here. This is a conceptual problem, and I know you guys love conceptual problems. Think about what happens here. The nitrogen gas is going to be mixing with the oxygen. The volume is no longer 2 liters. The volume is now the entire container, the 2-liter side and the 3-liter side. So the nitrogen gas actually expands to occupy a total of 5 liters. So we can answer part of this right now, that the volume of the nitrogen gas increases from 2 liters to 5 liters. Knowing that, I can now solve for the other half it's asking for. What is the partial pressure of nitrogen mixing? Well, don't freak out by the term partial pressure. That merely means it's a part of a whole. We know oxygen's the other half. Let's find what happens to the pressure of nitrogen. Nitrogen alone is going to be decreasing its pressure overall because it's going to be occupying a bigger container. This involves a gas law. We know that there is a relationship between pressure and volume. Boyle's law. Pressure times volume equals second pressure times second volume. Well, I should know the initial pressure of nitrogen. It's 1 atmosphere. I also know the initial volume of nitrogen. It is 2 liters. I do not know the ending pressure. It's what's going to happen and change. But I do know the final volume of nitrogen. It now occupies a total of 5 liters, and I see that here. If I solve for pressure 2, I have the other half of that question. Going into part B. Part B is quite similar. How does the volume of oxygen gas change when the gases mix? What is the partial pressure of oxygen in the mixture? So you'll be using the same method here. We see that oxygen starts off at a 3-liter side, but remember, when it mixes, the container becomes both sides combined. So the oxygen is going to increase from 3 liters to 5 liters total. It's also going to occupy the new side. But we can say something similar. The volume of the oxygen increases from 3 liters of its initial conditions to 5 liters of the final conditions. And once again, we're asked to solve for what happens to the pressure. We'll be using Boyle's law. We have P1V1 equals P2V2. I do know the initial pressure of oxygen is given to me, 2 atmospheres. I also know the initial volume of oxygen, being 3 liters. I can solve for pressure too, because I also know the final volume being 5 liters. So here, I also need to know the final pressure of oxygen. And that leads us to the final section, part C. What is the total pressure in the container after the gases mix? So far, we've only looked at each gas individually and separately. Total pressure is the sum of all the individual partial pressures. Well, I will need to know the pressure of the nitrogen after mixing, and finally, the pressure of the oxygen after mixing. These are what we were calculating earlier. Once I know the final pressure of nitrogen and I add it to the final pressure of oxygen, I will have counted for both pressures and thus the total pressure of the chamber. These are a few hints to solving 61.